Hey there! In this video we are looking at the definition of the derivative of a function. Now you may have looked already at the slope of the tangent line to a curve at specific points, but what we're looking at here is generating another function that gives the slope of the tangent line anywhere on the function. Alright, the derivative of a function is another function that gives the slope of the tangent line at any point on the function. This looks a lot like what you've, I'm assuming, seen before, which is the tangent slope definition. But the big difference here is we're leaving the variable as x rather than a specific value. In the past, you've likely found the slope of a tangent line at one particular value, and what you get is a number, a value at the end, but here what's going to result is a function, and that function gives the slope of the curve at any value of x. The definition is going to look a lot the same. You have the slope between 2 points that are really close together, except now we're going to use x plus h and x as our 2 points. In the past, you likely have found the slope at a single point. Maybe you said at 2, so you had f of 2 plus h minus f of 2, all divided by h. But here we want to know the slope at any value of x, so we're going to leave it as that variable x. And then important is to not just have this expression, because that's the slope of the secant line. You need the limit in front of it here to push those 2 points together, and then you have the slope of the tangent line. So the limit of the slope of the secant line between x plus h and x. And I don't think it would hurt to look at it visually again. So on a graph, what's happening is you have your point x. Now on the graph, it has to be a point somewhere. I'm calling it x, but it could be anywhere on the curve. And then you have a point on one side or the other that we're calling x plus h. And then we're looking at what's happening with the slope of the secant line as we make h go towards 0. It can be from one side or the other, and you can see that the slope of that secant line is getting closer and closer to the slope of the tangent line. And when h approaches 0, the slope of the secant line becomes the slope of the tangent line. Now there is an alternate definition, just like we had when we looked at the specific slope of the tangent line. It's also going to look similar. When we looked at a specific tangent line slope with this definition, we called this a and b here, f of b minus f of a over b minus a, but we need this to be a variable, so we're going to call it x and a. Now what we're saying here is this is going to be our slope, our tangent slope at a. So this is going to be the derivative at a, except you'll see that we'll be able to generalize it. It's similar to before. This just looks like the slope formula, right? If you had 2 points and you were going to call them something, likely you wouldn't call them x plus h and x like we do in this definition. Probably most logical people would call them a and b, or in this case, a and x. And what we're doing looks exactly the same when you look at it visually. Is you have the slope between 2 points that are called x and a, and then you're looking at what happens as the value of x approaches the value of a. So as those 2 points get closer and closer together, you get the slope of the tangent line. This is still the same thing here, just uses x and a instead of x plus h and x. Now, before we go any further, we're going to need to look at some notation for the derivative. There's actually lots of different notations that have been used over the centuries since calculus was first invented, but there are two that are primarily used today, and probably the only ones that you are going to use as you move forward with the study of calculus. The first of which is usually referred to as Lagrange notation, after Joseph Lagrange, an Italian-French mathematician and physicist and astronomer. But it actually was invented, this notation, by Leonhard Euler, who was a Swiss mathematician. So I put both their names there, despite the fact that it's normally called Lagrange notation. What we usually say for the derivative, their idea was if the function was f of x, we're going to call the derivative f with this little mark here, which you say f prime of x. That little mark is called a prime mark, and that's how they refer to the derivative, f prime of x. And this is probably the most common notation that's used today. If you are just using a y for your function, you can say y prime like that, y prime. And that's probably the simplest it could be, nice and brief, but it doesn't name the independent variable, just y prime, whereas this one, f prime of x, you know the function and you know the variable. Now, the other notation that's used was invented by one of the co-inventors of calculus, Gottfried Leibniz. His notation, he sort of thought of the slope, the way you think about slope, and used this dy dx, which looks a lot like how you write the slope, delta y, delta x, and he thought of these infinitesimally small quantities that you're comparing, and so he called the derivative dy dx. That's the symbol he used, and you just say it like that, dy dx. And one good thing about this notation is it names both of the variables. Now, another way of using Leibniz's notation is to think about this dx part of it almost as an operation. So sometimes you'll see ddx of f of x, of a function like that. And that's how you say it, ddx of f of x. And the good thing about that is, as you work through calculus, it emphasizes the idea that differentiation, finding the derivative, is an operation that you perform on a function. You find the derivative of a function. So that'll be more important later as you work through things. So you've got two different kinds of notation to use here. Now, sometimes when you're presented with options, you decide, well, I really like this. I'm not such a big fan of this, so I'm going to just leave that. I'm always going to use this one, never going to use that one. That's probably not the thing to do here, because they both have their advantages in different situations. You're going to use both of them all the time, and it's good to get familiar with both. All right? Let's look at some examples. What we're going to do for this first one here is use the definition of the derivative just to write an expression for the derivative for each of these functions down here. We're just going to write the expression. We're not going to follow it through and find the derivative. For this first function here, y equals cos x, y prime is going to be the limit as h approaches 0 of cos x plus h minus cos x. That's what the numerator in our expression there is, and then of course divided by h. As I said, we're not going to go through and find the derivative. If you were going to do that, you'd have to take this expression, use a trig identity for the cosine of the sum of two angles, and expand that and do some algebra and simplify it, and then you could evaluate the limit. Note, you can't evaluate the limit now because if we're looking at h approaching 0, we can't substitute in 0 there because we have divided by h on the bottom like that. For our second one here, y equals x to the fifth, y prime is going to be the limit as h approaches 0 of x plus h to the fifth minus x to the fifth divided by h. Again, if you were going to follow through and find that, you'd have to expand that binomial. You'd find that once you do that, you'll be able to cancel out some terms and then simplify, get rid of the h, and then you can evaluate it as h approaches 0. This third one down here, y equals 3 to the x, y prime is going to be the limit as h approaches 0 of 3 to the x plus h minus 3 to the x. Now you might think, wait, where's the f of x plus h? There's no brackets there. Well, the inside, if you will, of an exponential function is the exponent, and we don't write it with brackets when we write it like that. So that's what that is. And then, of course, divided by h on the bottom. Again, you'd have to do some work to do something with this expression where you can simplify and eventually get where you would be able to substitute in 0 for h to evaluate the limit. And our last one here, y equals x to the fourth minus root x. Y prime is going to be the limit as h approaches 0. With this one having two terms, each part of the expression on top is going to have two terms. So we have x plus h to the fourth for that first term, minus root x plus h for the second term, minus f of x, which is just x to the fourth, minus root x. And then, of course, on the bottom we have divided by h. All right? So as I said, you can't evaluate them as is for h approaching 0 because you have h in the denominator. But for all of them, there'd be different ways you would work with the top and eventually get to where you could evaluate the limit. All right? Let's look at another example. So here we're going to do the same thing we just did, but we're going to follow it through, not just write the definition of the derivative, follow it through and find the derivative for our function here, f of x equals x cubed. So first we have to start by writing the definition. So we're going to call it f prime of x because our function is called f of x, is the limit as h approaches 0. I'll just write the definition with f in it first, f of x plus h minus f of x over h. But then we can put the specific function in. So that's going to be equal to the limit as h approaches 0 of x plus h cubed minus x cubed, because x cubed is the specific function. And that's going to be equal to the limit as h approaches 0. We can expand this expression right here. And what that's going to give us when it's done and all simplified is that expression is going to turn into that expression. X cubed plus 3x squared h plus 3xh squared plus h cubed. And then minus x cubed on the end. And where we're going to go from there is we can simplify a few things here, because what we can do is we can say this x cubed and this x cubed add to 0, so we can cancel those out. And then we're going to say that this is going to be equal to the limit as h approaches 0 of just what's left over there on the top. 3x squared h plus 3xh squared plus h cubed over h. And now that we've gotten rid of those two x cubed terms, all the rest of the terms in here have an h in it, at least one, and so we can divide those out, those h's that are there. And so we can say that this is equal to the limit as h approaches 0 of just 3x squared, because we cancel out the 1h, we just have 3x squared there. In the second term, we got h squared over h, so we just have h left. And in the third term, we got h cubed over h, so we just have h squared there left, canceling out one h from each of them. Now that we've gotten rid of this divided by h on the bottom, now we can evaluate this limit by substitution. So we can substitute in 0 for h. We're not going to write limit anymore because now we're evaluating the limit. We're just going to substitute it in there. So for that h, that becomes 0, and that h, that becomes 0. So we've got 3x squared plus 3x times 0 plus 0 squared, which of course is going to be equal to 3x squared plus 0 plus 0. These terms both turn into zeros, and so all we have left is just this term. So we're going to say that our derivative is just 3x squared. All right, that's the derivative of x cubed. And again, what that means is 3x squared is going to give us the slope of x cubed anywhere on the function. As I said earlier, in the past, you might have found the slope of the tangent line but had a specific value in here. But now that we've left it as an x all the way through, you get an expression at the end, 3x squared, not a specific number. All right? Let's look at another example. All right, here we're going to, again, find the derivative of a function, but we're going to use the alternate definition first, and then we're going to do it again using the primary definition, and then we can compare the process. So this says differentiate this function f of x equals root x. Now, the word differentiate in calculus means to find the derivative of. It actually comes from Gottfried Leibniz, one of the co-inventors of calculus I mentioned earlier, and it just comes from the idea of finding the derivative is finding something that's going to be the slope of the function. And slope, you're talking about how the function values, the y values, differ for any given change in x. So the fact that you're looking at how it differs, differentials is a word you'll learn, and differentiate here means find the derivative of. So we're going to write here that our derivative, f prime of x, we're going to use that alternate definition. So the limit as x approaches a of f of x minus f of a over x minus a. And so with our specific function here, that's going to be equal to limit as x approaches a of root x minus root a over x minus a. And just again, we should note why we can't evaluate that limit at this point is because we want to look at what happens as x approaches a. So at some point, if we're going to do this by substitution, we're going to substitute in a for x. And if we substitute in a for x here now, it's going to be a minus a, which is 0 on the bottom, which we can't do. So we're going to have to do some algebra, and the technique we're going to use here is something you may have used in the past, maybe in a little bit of a different context, but we are going to multiply by the conjugate of this thing that's on top. And the conjugate of the thing on top is root x plus root a, right? If this is root x minus root a, the conjugate is root x plus root a. Now, we can't just multiply by that unless we multiply by that over itself, because then we're multiplying by a fraction that's equal to 1, and we're not changing the value of the thing. The reason that's going to work is because, as you maybe know, when you multiply out conjugates like that, it's just going to turn into a two-term expression here. Root x times root x is going to give us x. And the last two terms, root a times root a, is going to give us a. And those middle terms are going to cancel out. Root x times plus root a is plus root ax. And the other two terms, minus root a times root x, is minus root ax. So those two terms are going to cancel out. So what we're going to be left with here, this is going to be equal to the limit as x approaches a of, on the top, just x minus a when those two middle terms cancel out. On the bottom, I'm not going to actually multiply those out. I'm going to leave them as two binomials here. And the reason is because now what I can do is I can cancel this binomial with this binomial, right, which is why this method works. And that's going to leave us with this being equal to the limit as x approaches a of just 1 over root x plus root a. Now we're at the point where we can evaluate this limit by substitution and put in a for x. And so when you do that, this is going to be equal to 1 over root a plus root a. Notice this is where I stopped writing this limit because I actually evaluated the limit now and got this expression. And then, of course, you can write that as 1 over 2 root a. That's our derivative. Now, you might say, weren't we doing this with the idea that we were going to have an expression where x is the variable, and here we've got a being some specific value? Well, the thing is, a could be any value, right? So if the derivative at a is 1 over 2 root a, but if a can be any x value, we can just say that the derivative can be expressed with x as 1 over 2 root x. So that's our derivative. Our derivative is 1 over 2 root x. All right. I do want to go back here and just note one slightly different approach we might have taken with this, if you wanted to. At this stage here, when we had that, instead of multiplying by the conjugate and getting something you could cancel, instead what you can do here is you can factor this x minus a that's on the bottom. Now, what I mean by that, you might say, how can you factor that x minus a? There's nothing to factor. But in the same way that these two things multiply to this, you could factor this x minus a on the bottom as those two things. So you could do kind of the reverse of what we did there. And the reason why that would work is because once you do that, you can cancel that with that, and then you would just be left with the same thing here, 1 over root x plus root a. So then you'd be back to here. All right, so either way you do it, you get that the derivative is 1 over 2 root x. And let's just remember that the slope of the graph of root x can be determined with that function. All right, let's use the primary definition and see how that compares to this. All right, so we're going to find the derivative again for the function square root of x, but this time we're going to use the primary definition, and that definition is, of course, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And so with our specific function, that is going to be equal to the limit as h approaches 0 of root x plus h minus root x over h. And what we're going to do from here is we're going to do something similar to what we did using the alternate definition, and that is multiply by the conjugate of what's on top here. And the conjugate of that is root x plus h plus root x, right? Because this is a minus, so it's exactly the same thing with a plus there. And you're going to see something similar is going to happen here. Now again, note that we have to multiply it by that over itself so that we're multiplying it by a fraction that's equal to 1, so we're not changing it. And we're going to find that this is equal to limit as h approaches 0. When you multiply these two things on top here, the first term becomes just that times that is going to give you x plus h. And then the last term is going to be root x times root x, so it's going to be x. But again, the middle terms, the reason this works is the middle terms cancel out. That times that is plus root x times x plus h. And this is going to be minus root x times x plus h. So those two terms cancel out and you just have that on the top. And then of course on the bottom, I'm not going to multiply it out. I'm just going to leave it as h times root x plus h plus x. Now, what might be slightly different than what we did before is we're not going to be able to cancel out a binomial here, but what we can do is this x and this x, those add to 0, so we can just cancel those out. And so then this is going to be equal to the limit as h approaches 0 of just an h on the top and that same expression on the bottom. And then where we can go from there is we can cancel these two h's. And so that's going to leave us with this being equal to the limit as h approaches 0 of 1 over root x plus h plus root x. And now we're to the point where we can use substitution to evaluate that limit. And so that's going to be equal to, when we substitute in 0 for h, we are going to have 1 over root x plus 0, substitute the h for 0. Now, again, notice I'm not writing this limit anymore because now I have evaluated the limit. And then we can simplify that to just being equal to 1 over, this is root x. That's another root x, so we've got 2 root x on the bottom, which is what we got when we used the other definition. All right, so after all of that, I hope that you can both understand why the definition of the derivative is what it is, as well as how you can use the definition, or both definitions, the primary and the alternate, to find derivatives of functions.